Good morning, everyone. Good morning, guys.
Morning, sir.
How are you? Okay. Is everyone okay?
Mm-hmm.
Okay. Um, we're gonna continue with electrostatics, right? But before I start, I was having initially some issues. I couldn't have even the lesson with the grade 11s because the Zoom, I think it was updating or something. I heard they were talking about people hijacking Zoom, like people they just pop up, something like that. So I think there's a new update. So my system is was updating, so it's a bit slow, but I will try. I think now it's coming out right. Right. So if there are any glitches, then we might have to cancel the lesson, but I hope not. Right.
Yes.
Then, okay. Yesterday I posted like an assignment, like a consolidation activity for you guys to do. Did you see it? Guys, did you see it?
Yes.
Yeah. You guys, please just go over that. I think we'll discuss it on Friday. So I gave it up until tomorrow for you guys to do that. All right. So please go over the questions. It's out of 46. So go over it. Where there are challenges, please just send me a message. Then I'll assist. But I think it's kind of straightforward if you went over the magnetism. Right, so we're continuing. Um, we have electrostatics. Other sources, they define electrostatics as the field that studies charges that are stationary. All right, but another way to define it is electrostatics, study of imbalance of charge. We went over this last time. All right, so I'm just going to continue from there. Right, there are two types of charge. All right, we know there's a positive and a negative charge. So all objects surrounding us, including people, they contain large amounts of electric charge. All right. Like yesterday when I went into the bathroom, opened the tap on the sink. When I tried to wash my hands, I got a shock. I was not holding the tap. Just when I came in contact with the flowing water, I got a shock. Right. So it means there's some charges. There is some charges relative to the water in me. So it means we also have charges. Right. So all objects surrounding us, including people, contain large amounts of electric charges. So there are two types of electric charge. We've got a positive charge and we've got a negative charge. Right. A positive charge is carried by protons in the nucleus. Right, as we know when we looked at atoms. So we've got protons, they are found in the nucleus. Then we've got negative, we have negative charge is carried by electrons. So we find the electrons outside the atom. Objects can be either positively charged, right, or can be negatively charged, or they can be neutral, all right. Objects that are neutral, if an object is neutral, right, it means they are equal positive and negative charges. So it means your protons and your electrons are balanced, as in this example here. So here you've got 6 positive charges, those red positives. Then you've got 6 negative charges, which are those black negatives. So each positive and negative cancel. So that cancels, that will cancel, that will cancel. All of them are canceling. So the net charge here becomes 0. So if the positive and negative charges are balanced, then we say the object is neutral. Right. Then objects can change their charge by contact or by rubbing. All right. Neutral objects can become either positively charged or they can become negatively charged. So here We have, for example, the second example here, we have got 6 positive charges and 4 negative charges. So here there are more positives here and there are less negative. So the 4 positive will cancel with the 4 negative, right? Then we remain with 2. So your 6 plus negative 4 will give you a positive 2. That means the net charge of this object is a plus 2. So the object becomes positively charged. Then we come to the next one here. You've got 6 positive and you've got 9 negative, right? If you add the 2, 6 plus a negative 9, you get a negative 3. So the net charge is a negative 3. So this object is negatively charged, all right? Then we move on. We spoke about the charging of objects, right? So a neutral object can become charged either by friction or by just contact or by what you call rubbing, right? Rubbing, friction, almost the same, right? So here we spoke about ways to charge an object. We say charge can be separated by friction. We spoke about this in our last lesson. So electrons can be transferred from one surface to another by friction, right? But friction is not the only way. So charge can also be transferred by touching two different neutral insulating materials together. We spoke about this, right? This is called triboelectric charging. When objects touch and materials share electrons, or electrons are transferred from one material to another. We call it triboelectric charging. Triboelectric charging. Just remember the term there. So here we're explaining when two different neutral insulators touch each other, chemical bonds are formed at the place where they're in contact with each other. If atoms in surface A tend to hold electrons more tightly than the electrons in surface B, electrons will move from surface B to surface A, all right? So the one that is weaker bonds will lose electrons, and the one that's stronger will gain the electrons. This causes an imbalance in electric charge at the two surfaces. When the surfaces are separated from each other, surface A will have more electrons and the other one will have negative. We spoke about that one last time. Charging can also occur through contact. So we've got a positively charged perspex rod and transfer to a balloon or to another perspex rod. So the positively charged rod steals electrons from the other material, right? No friction is involved, right? This is where we we spoke about polarization, where we spoke a neutral material. If you bring a charged object, then positive will go. If it's the material that is brought is positive, then the positive will go to, will be repelled by the positive, and the negative will be attracted. Right. Then there's another thing. We have got what we call the triboelectric series. The triboelectric series. It is a series that is arranged materials, right? According to which one is going to gain, which one is going to lose electrons. So this triboelectric series can allow us to determine whether one material is likely to become charged from another material. Like the example that I spoke about last time. You take a ruler, you rub it on your jersey or you rub it on your hair, you bring it on papers. The papers are going to stick, right? Why do they stick? Because there's a difference of charge. Like charges repel and unlike charges attract, right? So materials from the more positive end of the series are more likely to lose electrons than those from the more negative end. So materials from the more positive end of the series are more likely to lose electrons than those from the more negative end. So right, like here, we've got glass and we've got wool, right? So if we rub glass on wool, right, then it means the glass will lose electrons and wool will gain electrons. That's how you use this series here, all right? So let's say you've got, last time it was plastic. I don't have plastic on this list here, but we've got paper here, all right? We've got glass. So if I rub glass and paper, all right, glass is very positive. and paper, according to the series, it's more negative, because the ones at the top are more positive. As we go down, then they are getting more and more negative. So if I take glass and paper, right, so it means paper is more negative. So when I rub the two, it means paper will gain the electrons and glass will lose the electrons. That's how you use that triboelectric series, right? Um, right? So when two materials are chosen and rubbed together, the one that is more positive in the series will lose electrons, and the one that is more negative in the series will gain electrons. For example, amber is more negative than wool, right? So if a piece of wool is rubbed against a piece of amber, then amber will become negatively charged. Right. So that's the example that we like the one that I've given you. So here we're talking about wool and amber. All right. So more negative wool. Wool is, for example, amber is more negative. So we've got amber here more negative, and we've got your wool at the top, which is more positive. So what is going to happen? Amber will gain electrons from wool. So wool will give amber the electrons. That's what we have. Okay, right. So that's how you use that triboelectric series for you to know which one loses or gains electrons when you rub, right, or when they come into contact. Right, then we look at the next one, forces between charges and charge conservation, right? So what do you have here? We know last time when we looked at magnetism, we're looking at poles, north and south. And we said unlike poles, they attract. And we said like poles, they repel. Here, the same principle holds here, right? But here now we are no longer talking about poles, we are talking about charges. Unlike charges are attracted to each other, and like charges repel or are repelled from each other. So if I bring a negative and a positive, right, the two objects are going to come closer, they're going to attract one another. So there will be an attractive force between the two. So they will come closer to each other, right? So we'll have an attractive force. Then the next one, we've got a repulsive force. If the charges are the same, negative and negative, they repel. So they move away from each other. We get a repulsive force, right? Same applies for positive and positive. So like charges repel and unlike charges attract. So that's what we have then. Right. Then we move on to the next one, charge conservation. There's a principle for conservation of charge. What does it say? It states that the net charge of an isolated system. What is an isolated system? It's a system where there is no exchange with the external environment. So whatever is in that system stays in. We have got what you, isolated system is also called a closed system. If it's a closed system, it means we have nothing goes out, nothing comes in. Just like now we're on quarantine. We were in level 5 lockdown. So it means no one leaves the country, no one comes into the country. That's like an isolated system. So we don't want contact with anyone from outside. So same applies here. We've got an isolated system. We've got a system which is closed. Whatever reaction is taking place, whatever is produced does not go out. Whatever is out cannot come in. That's what we mean by an isolated system. So we are saying the net charge of an isolated system remains constant. So if there is no exchange with the external, the amount of charge will remain the same during any physical process. All right. So e.g., two charged objects making contact, and two charged objects making contact and separating. So there is an equation for this. So the equation, what is it? You've got Q is equal to Q1 plus Q2 divided by 2. So if I've got two objects that come into contact, all right, let's say the other one is 5 plus 5, and the other one is 7. When they come, right, the total charge, you're going to add your 5 plus your 7 to give you 12. Then you divide by 2, it's 6. So when objects come into contact, right, they're going to share electrons up until electrons are balanced, or up until the charge is the same, then they separate, right? I'm going to look at an example now for you to understand what I'm talking about. Yeah. Right, so the formula that we have, we've got Q, the final charge Q is equal to the initial charge of object 1 plus the initial charge of object 2. We add that, then we divide by 2. That becomes the final charge of each object. All right, okay. Let's look at, there is an example here. So when two identical conducting spheres on an insulating stand are allowed to touch, they share the charge evenly between them. We can calculate the resulting charge using this equation here, right? So that's what we have here. We have Q, Q1, Q2. Let's look at this multiple choice question here. It says two identical spheres, right? Two identical spheres on insulated stands. Why the stands must be insulated is because we don't want the charges to be lost into that stand. So they carry charges of 3 microcoulomb and -5 microcoulomb respectively. The spheres are brought into contact with each other, right? Why do they come into contact? It's because this one is positive here and this one is negative, and we know unlike charges, what do? They attract, right? So they're going to be attracted to one another. The spheres are brought into contact with each other and return to their original positions. The charge on each sphere after contact is what? Right, so for you to do this, you need to do a calculation. Let me just open the board here and try and write something here. Okay. Right, so we have got our formula is Q, right, is equal to, right, we've got our Q1 plus our Q2, right, all over 2. Right, this is equal to, right, our Q1, that was the charge of 3 microcoulomb, right, microcoulomb, plus the other charge, I think it was minus, let me just check there, it was -5, right, -5. Right, so we've got a -5. Right, you've got your microcoulombs there, all over 2. Right, yes, someone is talking. Are you talking to me?
No.
Okay, right, then we have got, what are you going to do? You're going to add the 2, right? But here you've got a microcoulomb, right? You can convert the micro, we know what is micro. Micro, we said micro is equal to 10 to the power -6. So it's a millionth. It's 1 over a million, right? So we've got our millionth with 6 zeros there, right? So that's what you have, right? You don't have to convert here because our answer still is going to be that. If you want, you can do that. So you're going to have 3 multiplied by 10, to the power -6 plus -5 times 10 to the power -6 all over 2. You still get the same answer roughly. Right, so here we're going to add. We've got plus and minus, so it becomes negative. So we're going to have 3 minus 5, which becomes -2, which is 2 microcoulomb, right, over 2. We divide the 2, right? When you divide the 2, you get your answer is -1 microcoulomb. So what does that mean now? The two objects before, right? Before, one was positive and the other one was negative, so they attracted, because unlike charges, they attract. Then after that, our answer becomes negative. So we've got 2 spheres. We've got a sphere. We've got a sphere that is a -1, right? Then we've got another sphere that is also negative. right? So we see negative and negative, right? Negative and negative, they repel. So that's why the objects are going to touch, then they're going to separate. Just like when you take a ruler, you rub it on your head, right? You bring it to a paper, right? The paper is going to stick because the charges are not the same. So after some time, the paper falls down. Why does it fall? It's because when it was attracted, the charges there were different. So there was an attraction. During that contact, electrons are being transferred. How are electrons transferred? They are transferred from the one that is more negative to the one that is less negative, right? So in our case here, which one gave the other one the electrons? It will be our -5 is giving the 3 because this one is positive here, right? So electrons are moving from the 5, then they are going to the 3. Up until they balance, all of them, they become -1. So object A will be -1 microcoulomb, and the other one is -1 microcoulomb. They are now the same. There's no longer any transfer of charges. Then they split. So our answer is -1 microcoulomb, right? So let's check our answer, right? Our answer there. Right, so we check our answer, we got -1 microcoulomb, so the answer here becomes D. So the answer would be D. So that's how you use this equation here to find out what will be the charge, final charge after contact. All right, so objects come together, share electrons. When the charge is the same, then they repel one another. So that's what happens when your paper stick on a ruler. After some time, they separate because the paper and the ruler now contain roughly the same number of electrons, or they've got the same charge, right? Like charges, they repel, right? So that's what we have here, right? Then we've got another question here. Question number 2.1. A group of learners perform an investigation to determine the charge on each of 4 objects, Q, R, S, T. They use an object X with a negative charge as well as a neutral object P. So P is neutral, right? They make the following observations. So we've got observation 1, Q attracts P. Then observation 2, we've got R repels Q. Then we've got observation 3, S attracts R but repels T. Observation 4, T attracts X. All right. Then it says redraw the following table in your examination book and complete it. All right. So for 8 marks, we need to know, indicate what the charge on the object is. We've got positive or negative. So we've got Q, we've got R, we've got S. We need to know which one is positive, which one is negative. But the only clue that we're given there, it's a P. P is neutral, so that's a neutral object. So we know Q attracts P. So it means Q is charged, all right? Some polarization takes place here, right? Then observation 2, R repels Q. So we know the Q that is here, right, and R, they've got opposite charges. So R and Q have different charges. I want to try and see if I can write here. Can I write here? It's not writing here. Okay, let me just go back to my board there. Then I write. So we're going to start PQRST. Then we also have T attracts X. They use an object X with a negative charge. So here we've got a clue here, right? We've got a clue again here. They use an object X with a negative charge as well as a neutral object Q. So we have got, okay, let me just open my board here. Right, we have that. All right. Just want to just delete here. Clear. Right. Okay. Start again. Yeah. Right, so we've got our charges there. We start with P, we've got Q, we've got R, we've got S, all right? The problem, I have to go every time to the board.
Can't you multi-screen,
I can't I? Multi-screen.
multi-view, puts it side by side.
Okay, let me see if I can move this one here. Let me see. I have to minimize this. Let me see. If I do this, make it smaller. Okay. Let's see. So you can see all of them. Eh? So I've got my P, Q, R, S. Then we need a T here. So I'll put a T here. Right. Then we also have X. So X, we know X is negative. Right. And P, we know it's neutral. So P is just use a 0, neutral. Right. So we check for this one here. We know
You can't see what you're doing.
you can't see.
You can't see it.
Yeah, okay. Well, what do you see now?
We see what you were writing.
What I'm writing?
Yes, sir.
Do you see that? Okay. I think on Zoom, can I multi-share? Can I open a couple of? I think I cannot do that here. Can I open two things at a time? No, it's not allowing me here. Okay. What must I do now? Screen share. Let me see. Yeah. Okay. You see the question now, ne?
Yes, sir.
But I can't do writings here. This won't allow me to write here. Okay. All right. So what I'm gonna do? Maybe I must leave this question for you guys to do it. Is it fine?
If you explain.
Yeah. Or should I carry on
Explain, sir.
explaining?
Yes, sir, please.
I must explain.
Yes, sir.
Okay. All right. I'm having a challenge trying to. Technology is beating me here. Okay. All right. Fine. Let me just. Can't see this. Can you see the? Yeah. Yeah.
So can't you screenshot the screen and then draw on the screen?
On the screen, yo. Let me
Screenshot
see.
it and draw it.
Yeah.
Windows
Let me
and
see.
print key. Windows and print key.
It's what?
Windows and print key. Then you go to pictures.
Yeah. Okay. Let me see. It's what? Windows and what?
Print key.
Print
It's
key.
PRT. It's at your right top corner.
Right top corner. Okay. I can't see this. What must I press?
Windows key.
Yeah.
And on the top right corner, there's PRT SC system. Or, in other words, print.
Print. Oh, okay. This one. But I see our time now. It's only 10 minutes left. Let me leave this one. Otherwise, it's gonna be another lesson now on computers. But it's fine. Let me leave it. Yeah, let me leave it. You guys will do this one. Let me just continue here with what I wanna do here. I think I'll try to up my game in our next lesson, then I'll show you. Okay, I'll leave this one for you guys to play around with it, then I'll discuss it in the next class. So let me just move on to the next one. So it says 2.2, two small metal spheres, B and C, on insulated stands carry charges of 3 times 10 to the power negative 9 coulombs and negative 6 times 10 to the power negative 9 respectively. So this is what we have and the other one. So it says how does the number of electrons on sphere C compare with the number of protons, right, on sphere C? Right, choose your answer from one of the following: less than, the same as, or more than. All right, so how does the number of electrons on sphere C compare with the number of protons on sphere C? So we're just looking at sphere C, which is negatively charged. How does the number of electrons compare to the number of protons? Since it is negative, what would be the answer there?
More.
Huh? Right, more than. Right, so the number of electrons on C is more than, because it's negatively charged. So that's the correct answer. So the answer is more than. Give a reason for your answer to question 2.2.1. What would be the reason here?
The object is negatively charged, therefore stating that there's more electrons.
Right. Since it is negatively charged, so it means there are more electrons than protons. So that would be the reason there. Right. Okay, we move on to the next one. Calculate the number of electrons on sphere C. Right. For you to be able to answer this question here, we need to look at the following first. Then I'll come back to this. Right. So we have got what you call, okay, let me just go over this. We've got conductors and insulators. Right. Conductors allow charge to move through them easily. Right. Because there's charge can flow. Right. Insulators do not allow charge to move through them easily. So we've got conductors. They are conductors because they are able to transfer charge. Right. And here, most of the conductors are metals because they've got electrons that are free to move. They've got delocalized electrons that can move, right? For example, you've got your insulators. Insulators are substances that do not allow electricity to pass through. Why? Because there are no free electrons. There are no free electrons. Another example is an ionic compound, where you've got an ionic compound, like you take salt, sodium chloride. If you take sodium chloride, you have got ionic bonding, right? In that ionic bonding, for example, let me just explain here using this. Let me just show you this. So let's say you've got sodium chloride, right? NaCl, right? I don't have to put the charge here, but when you sodium chloride, when it's a solid, it does not conduct electricity because there are no free electrons here or free ions. But when you put it in water, aqueous, you put it in water, right? Now you've got your sodium plus and you've got your chloride ions, which are aqueous. Then now if you connect a circuit to this, electricity is gonna flow. Why? It's because you have free ions. So this becomes your free ions. These are your carrier of charges. So that substance will conduct electricity. Right. So that's what you have then. Now here you've got your insulators. Insulators, there's a covalent bonding, right? So there are no free electrons. So insulators do not allow charge to move through them easily, right? So conductors, free charges can move, and insulators charges cannot move. Right, then you've got the quantization of charge. Quantization of charge. Charge is measured in coulombs. So we use C for coulombs. So you see, like in the example that we looked at the top there, it's written here 3 times 10 to the power negative 9 C. So the C is the units for coulombs. Yes.
You cannot see what you're saying.
Okay. 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 Right. Can you see now? Hello?
Yes.
Okay, so I was explaining here conductors and insulators, right? So I'm saying insulators do not allow charge to move, to pass through them, and conductors allow charge to pass through them, right? So we have here quantization of charge. Charge is measured in coulombs, right? So C represents your units, coulombs. Charge is quantized in units of charge of an electron, right? So in other words, charge goes in certain multiples of charge. We know the smallest charge is the charge that you find on an electron, which is 1,6 times 10 to the power negative 19 coulombs. That's your smallest charge. So your charge, anything else, it's a multiple of this charge, right? Just like when you go to, for example, you go to the shop to buy your sugar. The smallest sugar, maybe packet will be 250 grams or 500 grams. Anything else becomes multiples of that smallest quantity. So you can get maybe 1 kg, you can get whatever multiple of the smallest. That's the same thing that happens with charge. So the smallest charge is 1,6, right? So here we have the formula. When you use the formula, we've got Q is equal to NQE. So for you to get the charge, you have to know how many electrons are there. So N represents the number of electrons, and Q represents the smallest charge, which is your charge on an electron. So for you to get charge, you have to know the number of electrons multiplied by the charge on electron, which is 1,6 times 10 to the power negative 19. All right. We know a proton is the same charge and an electron is the same charge. The only difference will be a negative or a positive. Right. So going back to this question here, calculate the number of electrons on C. So on C, what we're gonna do? You guys will have to finish up this. My time, I only have about 2 minutes left, but I'll just explain what is it that you must do. Right. Calculate the number of electrons on sphere C. So you're gonna go to sphere C. This is the charge that you have. Right. What are we looking for? We're looking for number of electrons. So you're gonna use your equation. The equation that you're gonna use is Q is equal to NQE. So where there's Q, you substitute it with the charge that is on the sphere here, which is -6 times 10 to the power -9, right? Then you go to your N. N is what you're looking for. You're looking for number of electrons. And QE, what is QE? QE is the charge on an electron. Then you make your N the subject of the formula. That becomes the number of electrons on the sphere. Right. So that's how you answer question number 2.2.3. Then the rest here becomes your principle of quantization of charge. You guys, I would like you to go over this. Then we'll discuss it on Friday. Is that fine?
Yes, sir.
Yeah.
Right, sorry about the glitches here. I can't exactly show the calculations here. I've got less than a minute. Yeah, guys, let's meet again on Friday, same time. Is that fine?
Yes, sir.
Yes.
Yes. So I'll
Sir.
send this. So please go over it and do some calculations. Any challenges, send me a message, then I'll respond.
Sir,
Yes.
can you please scroll up, sir?
Can I? You want to?
Scroll up.
I'm a scroller. Okay, my time is up here. I'm
Yes.
gonna be cut anytime soon. I'll post this, but you can send me a message. My time is up. Let's meet in the next one. Or send me a message, Tokozis.
Yes, sir.
All right. Okay, let's meet on Friday. Anything, please ask. Bye.
Yes, sir.
All right. Ciao.
Sure.